Hey, so just a couple of reminders, okay, because you guys will have a little quiz at the very end of the period. So a couple of reminders, probably want to listen to this, was that Mendeleev, how did he organize the periodic table? By mass. Good. Moseley is the one who came around and he ended up doing it by atomic number, and that's what ours is by today, okay? Okay. Your metals, just a reminder, we're going to talk a little bit more about our ions today. So metals tend to be your cations. They're positive, so they give away or take electrons. They become positive, so they give away their electrons, okay? And then your nonmetals, which are anions, become negative, so they take electrons. Good, nice work. Okay, just a little reminder of your different families. So group 1 is your alkali metals. Are they the reactive ones?
No.
Yes, very. I still owe you that video. You're right. I'm sorry. You guys didn't know that. Okay, so they're very reactive. I'll show you guys that video today. The alkaline earth metals are group 2. They're kind of reactive, but not as much. And then we have our transition metals in the middle. And then who's in group 17? Halogens. And who's in group 18? Okay, do noble gases like to bond?
No.
Are they reactive?
No.
No, because they're stable, right? But group 17 is very reactive, group 1 is very reactive, okay? Why are these last two little rows down here? They can't fit. Good, awesome. Yes. All right, cool. Go back to this page now. So this was after you guys looked at all of your periodic tables. We kind of filled in your different trends on this. So this should just be a review, and so I'm expecting you guys to kind of just shout out your answers there. But one thing that I am going to change up is that now I'm going to also ask you to fill in or tell me, is it because of the shielding effect? Or is it because of Zeff? Okay, so if you look on the board, I have our objective statement. And so remember, one of our big ideas was we talked about Coulomb's law on Tuesday. Okay, and that's the attraction between positive and negative things. And I told you guys that when you go to look at these trends, when you go to memorize them, you need to know why they're occurring. One thing is the shielding effect. Who remembers what that's related to? The amount of shells. Good, all right. So do you think that happens as you move down a group or across a period? Down a group, right? Because that's when we go to the next energy level. So we add a new shell on there. So that's shielding effect. That's your up-down argument, okay? When you are talking about Zeff, that stands for effective nuclear charge, okay? You might be writing these at the very top of your page, by the way. There is, but we'll do it later. Just write them here for now. All right, so effective nuclear charge. What do we know the nucleus is charged as? Positive or negative? Positive. It's positive. Why? Because it's full of a lot of protons. Yeah. Okay, so when we're talking about effective nuclear charge increasing, are we talking about across the row or increasing energy levels? Across the row, exactly. And what's our evidence of that? What number is getting bigger as you move across a row in the periodic table? The atomic number, right? And your atomic number, we learned at the very beginning of the year, 8-man, right? Atomic number is your number of protons. And that was the one that I told you is guaranteed for the rest of the year. Electrons, it kind of switches up if it's not neutral, right? Yeah. Okay? So, all right. So knowing that, we're going to stop at each one of these periodic tables again and make sure we've got that, okay? So you guys should have already had written in here, how many electrons does everybody want? 8. Okay. Your atomic radius is just the size of your atom. As you go across the periodic table, are you increasing or decreasing size? We are decreasing. Okay, and as you move down your periodic table, you are increasing. Okay, and when we are decreasing, actually, let's start with the easy one. As you are increasing going down, why? More shields, more shells, right? So it's their shielding effect. So put shielding next to this guy if you hadn't already. Okay, that's your shielding effect. Why does it decrease going across? Yes. More protons. What does that do, though? If I have more protons,
Pulls in electrons.
pulls them all in. Yeah, you become a super magnet. That's what I want you to think of. Okay, you're like a super magnet. If you increase that protons, all of that force goes to each individual electron, and they're all just pulled in really tight. So decreasing because of, we're going to put the short version, which is Zeff. If you're wondering what Zeff, where that's coming from, by the way, Z is your atomic number, technically, and the F part is effective, so it's effective nuclear charge. That's what it's talking about. Yes, ma'am.
Wait, okay, so it's increasing in protons, right?
Right.
But as you go this way, it's decreasing.
So as it increases in proton, the atomic radius is smaller because the protons pull the electrons closer to the center.
And then you move to a new row and you add another shell. So now you're already bigger. You just got a little bit bigger, and you start that trend over and you get smaller, 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 smaller because you're increasing protons. So just what he said.
So as you increase protons, your what is decreasing?
The radius.
Your radius decreases. Yeah.
Okay.
Yeah. Your radius is decreasing because your Zeff is going up. Is that better? So your proton charge is going up. That attraction is going up. You're turning into a super magnet by the time you become fluorine. Okay? All right. Cool. For ionic radius, okay? For ionic radius, this was also your size of common ions. Where was the special line on this one? Metalloids, right? So we kind of made a little squiggly here. Who was on the right side of my metalloids line? Are those anions or cations? Anions. These are your anions. These guys are negative, okay? Which means they gained an electron. So your little visual there. So you have a little nucleus and you have your little electron cloud and it's kind of fullish. And then you try to throw another electron in there. If you throw another electron in there, do they want to be anywhere near each other? No, so they poof out. They repel each other. And they get really, 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 really big. So your anions tend to be the big guys when you compare them to a cation. Okay, so those guys poof out, and the biggest one on there is carbon, and that's because it accepts 4 electrons. So imagine shoving 4 into that, right? They're like, heck no, you're not gonna be by me. So they just completely spread out. Okay, and then down here on the left-hand side of your metalloids line is your cations, right?
Wait, I thought as it went more to the right, the radius got smaller because there's more protons.
Yes.
But you're saying that it's like poofing out.
That's just an anion. It's just the trend is still the same. Okay, hold on. We'll get there. Don't worry about that yet. Okay, so your cations, and we're going to put this on another page in just a second, but your cations become positive, so that means they gave away an electron. When they gave away an electron, that means you just increased their positive charge. They just became a supermagnet, so they shrink in. That's why cations are going to be tiny, anions are going to be huge. Now, metalloids line was important to us because you cannot compare a cation to an anion. You just can't, okay, when you're talking about your trend. So remember, the same general trend is still occurring, and that is that as you move across, you are still decreasing size, okay? As you move down, you are still increasing. The special part about this is that you have to start over at your metalloids line. And so it's still shrinking. It's just you had to start over right when you started the non-metal side, okay? So it's still stuff, the same stuff is still happening. It's just when you become an anion or a cation, that means you're messing with your electron cloud. You're either giving something away or you're taking one in. Yes, ma'am.
Okay, so
Okay, all right, so moving on. Ionization energy, okay? Ionization energy, if you remember, was the energy required to remove an electron, okay? And so as we go across for ionization energy, it increased or decreased? That increased, okay? Who has the most? which column, which group has the most ionization energy?
The noble gases.
The noble gases
Already
do.
full, so they don't want to give anything away.
True story. Awesome job. Yes, they are already full. They're stable. They're happy. They're not going to let you take something away. As you move down a group, you're going to decrease to where francium, does he even have ionization energy? No, he is handing it to you and saying, take my electron, all right? So if you remember, we use the heart thing to help you with this trend. So big heart in the top left, top right corner, little heart in the bottom left corner, okay? Now, let's put this in terms of the Y. Why is it increasing going across?
So they get getting more.
Did they get that right?
Because their outer shell is full.
That's your answer. Are we clear? You only got those two answers. It is either Zeff or it is shielding effect. When you move across, what are you gaining? The other one.
I don't know.
Losing all those shells.
I'm gonna be quiet.
Stop, y'all. Atomic number is getting bigger. Who are you gaining going across? Protons, right? When you are gaining protons going across, or you are increasing the number of protons that you have, you just became a what when you got to the fluorine side? A supermagnet, right? That is holding on to all of its electrons super much. Do we hear that? We're good? Okay, so it will not let you take any kind of electron. Francium is at the bottom of a group. Okay, and he's also on this side. So small atomic number in his row, but he's also at the bottom of a family. Why is it decreasing going down?
Because as you go down, your atomic number gets bigger, so have outer shell.
There's two answers, shielding effect or Zeff. You guys had it. Shielding effect. Because you are increasing shells, you just increased your distance. So are you a supermagnet when you don't have any, when you're not close to each other? Remember, if you have a magnet and you're holding them really close to each other, are they going to stick? Yes. Are they going to stick if you hold them an arm's length away? No, they're not even going to, you're not even going to feel that force. That is francium. That is francium right there. And so that's why you can walk off with its electron and it won't even know. Okay? Are we all clear on that? Okay. This is painful.
I have an excuse.
Okay, so electronegativity is an atom's ability to attract electrons. So this is very specific to bonding, okay? Okay, we don't even care about noble gases because they're not supposed to be bonding, okay? We will see later one of them does, but don't worry about that. Okay. Who wants those electrons so much? There is only one atom up there that has the biggest electronegativity. There's only one element. Who is it?
I said the F one.
Yes, the F one. Good. Fluorine.
Oh, yeah.
Fluorine had the 4.0. What did francium have? Who remembers?
3.9.
0.7. Not even 1. Okay? So big heart in fluorine's corner, little heart in francium's corner. So as we are going across, we are increasing. We are getting bigger. Electronegativity.
The reason fluorine wants it more than the other people in its group is because it has more Zeff.
Correct. Great job. Nice work. Yes, it increases because it has more Zeff. It has more protons in that row, and it's a tiny itty-bitty radius, right? So because of that, because we have more nuclear charge, we are holding on to those electrons like a supermagnet. Francium, on the other hand, it's decreasing going down the group because of shielding. We have increased that distance so much, it doesn't care about its outside electron. Yes?
Doesn't cesium actually have a lower electronegativity than francium has?
I don't know. You'd have to tell me. Okay. We're just getting the trends. Okay. All right. So what I want you guys to look at is the big picture now.
Yeah.
The big picture. Which two have the same trends?
The top two.
The top two and the? Good. Radius is the same trend. All of this stuff is the same trend. That's why I used hearts for the bottom two, and the top ones I put the B and the S, okay? So radius, when you're talking about size, has the same trend. When you're talking about that love of electrons, you have the same trend. It doesn't change. So if you can chunk those together in your brain, it'll be easier for you to remember these. What did you also notice was the same on every single one of these? Zeff was going across or up and down? Across, and shielding was going up and down. That's your argument for every single one of these. So if I ask you why, you have to look, is it a trend going up and down, or is it the trend going across? Okay? Ones that are in the middle, you kind of combine both. Okay? And you just say it's at a lower energy level and it's halfway across. Okay, if you're comparing it to something else. And you'll, trust me, you'll know it when you see it, okay? But I want you to see big picture is those top two are the same, bottom two are the same, arguments are the same. Don't sit there and try to memorize individual things. It's not worth it, okay? Cool. Turn your page, or I think maybe pack it. Maybe just flip it over, yeah. All right, I want you to see that you have all this information. If Miss Vogel's version wasn't very clear, you guys have it, okay? So I just wanted to show you that you have your definition for effective nuclear charge, if you would like to look at that. You have atomic radius, and it tells you that it decreases across the period, increases down a column, and then it gives you a visual at the bottom. It is an easy read, so I do recommend that if you do not feel very confident on this yet, read it. Read it, okay? Because it's a good resource for you, okay? Over here on this side, I am going to take a second to talk about that ionic radius that we all got lost on. Okay, so if you notice, who are my guys to the left of this little line? Are they showing cations or anions? Cations. Remember, the easy way to remember that is cations has that T right there in the middle. Looks like a positive sign. Okay. When you are showing a neutral thing turning into an ion, what do we notice about cations? They all got smaller. Exactly. Okay. They get smaller. This is, now just so you know, when you're worried about ions, it's when you are kind of in the midst of bonding, okay? So you're becoming an ionic compound with something. That's when everybody starts stealing electrons from each other, okay? So you guys aren't there yet, but I just need you to know that this does not happen just across the periodic table. It doesn't just magically turn into an ion. That's not what goes on. It's when we start putting things together, okay? So it gives away an electron. So what you just did is now you made your protons more than your electrons, right? If you make your protons more than electrons, you just became a supermagnet. Supermagnet, okay? Just like Zeff. Just like that Zeff argument. Okay, so you squeeze them all in. So if you notice, they all got smaller. Okay? Okay, what do you notice is to the right of this little squiggly line? These are anions. Okay, these are the negative ones, meaning they gain electrons. Okay, so these lose electrons. These gain electrons. And this is all written, by the way, underneath, so you can also read it there. Okay? But your anions, what do you notice happens to them when they become an ion? They get bigger. Why? Because those electrons are repelling each other now. They're repelling the excess electrons that don't belong there. Right? So once again, this only happens once you start bonding and all that stuff. So don't worry about like when this is occurring. It's not just like I'm holding a fluorine atom and all of a sudden it became an ion. No, that's not what happens. Okay? Okay. So what you do need to know this though for testing purposes is that cations will become smaller, anions will become bigger. If you do not want to remember all the science-y stuff that I just blurted at you, okay? An easy way to remember this is if you throw up an electron, you got really small. If you gobbled up an electron, you got really fat, Okay? So please remember that. You get fat if you, well, okay, or I was just going for like, you know, if you lose when you get skinny, if you gain when you get bigger. Okay, anyway, okay, so you can use the eating analogy on that one. All right, so this just shows you exactly what I just said right there, okay? And then this explains what ionization energy is. Ooh. And it tells you that it increases across the period. And on the other side, it'll tell you that it decreases going down the group. Okay? These are worth reading as well if you really don't feel clear on it. It connects it to electron configuration. Okay, the page over. Okay. Ionization energy decreases down a column or group. And then down here it talks about electronegativity and how it is a property which measures the attraction of an atom to its outer electrons. And it tells you that it increases in a period, decreases down a column or group. And those little explanations below the parts that I highlighted tell you the Zeff and the shielding arguments. Okay, so it kind of puts it maybe a little bit better of a visual. All right. I also just wanted to show you that you have this, okay? I would say things to recognize on these would be any kind of electron configuration. So whether it's in the S group or P group or D group, whatever. And so like, for example, this guy says they're the S1s, right? So know that. I would know who's reactive. Okay, so you can put little stars. You do not need to do the real world applications. I don't care about that right now. And then any distinct characteristics. So when you go to study at home, that's what I would look for in all these and highlight those things. Okay, so when I say distinct characteristics, I mean like soft, hard, colored, not colored. Okay. And so those would be the things to look for in that little chart. Otherwise, we kind of went through some of it. So, okay. So once you're good with that, go ahead and flip your packet over. We are now going to apply everything that you've learned. We're going to practice it for a little bit, and then we're going to take that quiz at the end of the period. It should only take you guys about 7 minutes max to take it. It's 5 quick multiple choice questions, so we'll go until that point. So the page that you're looking at, this was what I had assigned for homework to start on. So if you did, cool, I have an answer key and you can come check your answers on mine. If you didn't, then today you're practicing, okay? A couple things to point out. These are not multiple choice. You are going through each one and saying which one is bigger, okay? So remember, bigger, smaller, what chart or what trend are we thinking about? Radius or loving electron stuff? This is all radius stuff, okay? When I say two elements are similar in chemical properties, am I talking about rows or columns? Columns, so we're talking about groups, families.
Those are the ones that go up and down.
Correct. Okay, and then the rest of these really lay it out for you. They tell you ionization energy and electronegativity. Just remember those guys are your hearts. Okay? All right. So I'm going to let you guys work together. And like I said, if you need to come check it, do that. If you have already finished this whole page, you check your answers, and then you move on to the next side, which are a little bit more challenging. You got to do a little bit more thinking, okay? But that should be pretty good. Apply what you know. You guys got this. I believe in you. Oh, wait, I do want to point out one more thing. Sorry. I want to point out what you guys have on the last page in your packet, and that is this, okay? It's very, very helpful in my opinion. You guys have this on the last page. What this has is this has your two trends on there, right? So big radius, little heart, and in the top corner it has the big heart, little radius. And it tells you that your argument always going across is Zeff, your trend going down is always shielding effect. One of my AP girls made this, and the back has even more information. So we are going to put this page into your journal, not today. I would wait till maybe tomorrow or Monday, okay? But this is a really useful page for you guys. So you can use this while you guys are working out your trends or work on a blank periodic table, okay? All right, that's all I got.